Today in this video, we're going to be talking about what are called the measures of variation. And when you think about measures of variation, you should think about the word variation and what it means. Variation would be how much does something vary. So when you're looking at data, how much does the data vary? That is the idea of this. And we're going to be looking at, well, how do we measure that? And I'm going to start off with an example here. It may not be a great example, but I'm hoping you'll get the idea of this. Let's say we took the senior class and we get all the heights of the entire senior class, or maybe just the heights of a good sampling of the senior class. And we plotted them out. What you'd end up with is you'd have an average amount for the population. And there'd be a lot of those people. This is the number of people. This axis here is just how many people had that particular height. So whatever the average height was for that senior class, well, you'd have a lot more people close to that. Out here on the edges, though, going this way, this is the taller side. Well, you'd have fewer and fewer people, and you'd end up with that, one or two really tall people. Just a couple of people, nothing like compared back to here. And then on the short side, kind of the same argument. You get that one or two really short people, not very many real short ones. Most of the people, they're back here. But then if we compare that to the entire school, of course, you'd still end up with an average. And I already mentioned I didn't really like this graph because obviously the average here is not the average height. Here we're talking about the numbers of people for the average of that. I know the averages themselves wouldn't line up. But just go with me on this. We would have, of course, a lot more people close to the average, so this curve, this distribution is going to be a lot taller. But the other thing we would have larger numbers way out here towards the end. Now, we still just have that one or two tallest people, which may or may not be in the senior class. Maybe it's in the junior class. It obviously would be one of the older classes. But notice that on the short and the tall side, how much farther out it would be. And so we would say that if you look at the heights of all the students in a school, that there'd be a lot more variation, which just sort of makes sense because you're going to have a lot shorter people in those younger grades. So you're going to have a lot more variation in the entirety of the school than looking at just a single class. And that's the topic of the day, variation. And then how do we measure that? How do we describe the variation from one data set to another data set? Well, we have different methods for measuring this spread. The spread is another way of talking about the variation. First is the range. This is the easiest one. Let's take a look at this blue graph right here. You're going to have a lowest number. You're going to have a highest number. And those two numbers describe how spread out the data is. It's a very simple way of describing the variation or the spread. And in this case, spread is probably the better term than variation, because even with this, it's tough to actually describe the variation. It's kind of the ideas there, but spread is probably the better word. It's just the difference, so you subtract. You take the most, you take away the least, and tells you the difference between the greatest and the least. Very easy to calculate, not necessarily useful all the time. Then we've got another one called variance. Okay, we're doing measures of variation, so variance seems like a word that would make sense. The description of it's not going to make a lot of sense to you right now. This is one of those things that the more you use this, the more it'll make sense to you. The mean of the squares of the deviation from the mean. To deviate means to be away from. Okay, so let's say that if we just go right here to the mean, let's say the mean is right here. Okay, well, you're going to have some data that's farther away from the mean. I'm on this green one here. And then some data that's closer to the mean. So this deviates more than this deviates. Then we got this term, the mean of the squares of the deviation from the mean. So this is a little confusing. These are two different means that they're talking about. What it's saying is, what's the average squared distance from the mean to each data point. And I'm going to demonstrate this to you further in just a couple of minutes here. Hopefully it'll make more sense than as we go. Then we've got the standard deviation. The standard deviation is related to the variance, and there's that word to deviate again, standard deviation. It's the average amount at which an individual item deviate from the mean of the data. These two things are related here. I didn't read this on purpose because I wanted to kind of tie these together. When you talk about variance, variance measures the average degree to which each point differs from the mean, and the units are a squared version of the units of the mean. Again, I'm going to have a little thing that I'll show you in a minute, hopefully make more sense of that. But then the standard deviation is literally the square root of this. Whatever you get here, you take the square root of that, and you have what's called the standard deviation. In the long run, we end up working a lot with the standard deviation. Out of all of our measures of variance, this is the one that we truly use a ton. We use this a little, we use this a little, but you can't forget that these two are actually related to each other. And I'm going to show you that equation-wise in just a couple minutes here. Okay, so range. Let's go back to the range. Again, it's just two numbers. They're kind of useful, but not really useful. They're really, really sensitive to outliers, because if you have an outlier, it's going to be one of the two numbers. Again, if you got a least, and then say a lot of your data's in here, and then you've got one outlier way out here. Well, because I'm only describing the difference between these, I really don't get a feel for the fact that this one data point is a long, long ways away from all the other data points. It is easy to compute, so that's nice about it. It's easy to understand. Here's a couple of box and whisker plots. And in this case, the range, again, is just the least, the difference between the least and the most. So this is at 29. This is at 18, so the range here would be 11. Real simple to calculate, pretty simple to understand. Again, the range for this would just be the least to the most, and then you find the difference in between. Variance. I found this little graph online. I like this. We've got fulcrum here. We got some sort of weights on this balance here, and of course it's nicely weighted out right now. And here it's still weighted evenly, not weighted out. This one's weighted evenly as well, but notice that the variance, how far spread out they are, is much, much smaller. Variance is going to be a measure of how spread out they are. And we get this from what process called the least squares fit. Now here is the equation for this. And what it is, this is going to be, so this is the Greek letter sigma. Sigma squared is equal to the sum of, this is going to be the data points value. Take away, this is the mean value of the population. Quantity squared, and you're going to add these up for all of the data points. So on each data point, you'll find how far away it is from the mean. I can actually show you this on this. This is a piece of the graph here. Here's this line right here represents the mean. So that's your population mean. And I find how far away is the data point from there. And then when it says squares, like we're literally making squares. We're taking that distance, we're squaring it to get that area right there. Okay, so that's what this is doing. You find the difference between the mean and the data point. That's how long this is. Then you square it. Okay, so we are going to get the area of a square. Then you're going to add up all of them. So for all the data points, you get all these squares. Some are big, some are small. Depends on how far away they are from the mean. And then you're going to divide by how many there are. So that's in that definition I gave you. It was the mean of the squared distances. So we're dividing by how many, we're finding the mean of that, or the average of it. If it happens to be for a sample, then this is the symbol. And you're going to want to start keeping track of these symbols. I would get a cheat sheet. If you do not have a piece of paper, please pause this and get yourself a sheet of paper, because you're going to want to start keeping track. We're getting a lot of symbols here, a lot of equations. So we're going to have the sample variance, that's this right here. it looks close to the same, but instead of the population mean, it's going to be the sample mean. Still going to find the difference, still going to make squares, so we're going to square it, still going to add up all of them squares, but then we're going to tweak it. It's not the divided by how many, but n minus 1. This is a very strange thing. In a previous lecture, I made the statement that statistics have been developed through trial and error, error, error. This is one of those weird deals where it seems like, well, you would just divide by n to get the average. As people were developing statistics, though, they realized that the sample variance was always off by just a little bit. And for some crazy reason, somebody, I don't know who, came up with the idea of, instead of dividing by n minus 1. And it fixed the problem. And so that ended up becoming the permanent version of this particular equation. All right, so I'm going to take you to just a little demonstration here real quick of what I'm talking about. This is a least squares fit. So again, what you're looking at here, the blue line right here represents the mean, okay, the slope. And later on this year when we do regression, we're going to be looking for the line of best fit. If you're familiar with that term, this would be our line of best fit here. The little blue dots are the data points. And then we've got a distance to each one of them. Now, what this represents here is the sum of all of the squares. That's the summation of, x minus mu quantity squared. So this is the point. This is, again, is your average, the mu, that u-looking thing. If I change one of these, of course, changes the sum of the squares. And so we could have all the points stacked up real close to the mean. And in that case, our variance is going to be small. Now remember, to actually get the variance, we have to take and divide this by how many data points there are. But I think you get the idea here. As long as they're all really close to the mean, you don't have very much variation. But if they're just scattered all over the place, well, then it's different. Then you're going to have a lot of variation. So your variance is going to be a much bigger number. So that hopefully gives you an idea of what variance is. Now, when we get to the standard deviation, all the standard deviation is now you still go back and you take the square root of the, after you've divided this by how many are, then you take the square root, which is giving you a version of the average distance back. And that's what that's going to be. So let's get to that. Again, the next thing is the standard deviation. Oh, I need to make this comment real quick before I move on. The sample variance, so that's this one here, is an unbiased estimator. In other words, it's not biased easily. When you have biased data, it doesn't get pulled along with it easily. Not saying it can't be, it's just not easily pulled away. It's an unbiased estimator of the population variance, which means it tends not to underestimate or not overestimate the population variance. Put that in your notes. The sample variance tends to not underestimate or overestimate the true population variance. Now, I know you've got these formulas here, and yes, you could write these down, but I don't need you to write them down because in your calculator, at this point, hopefully you've already learned how to enter your data and go to single variable stats. Under single variable stats, you can see right here, this right here. That is going to be your sample variance. So you can find it right there. Now, it does not give a population one. The reason for this, we don't calculate variance very often. And when it is calculated, you're almost always dealing with a sample anyways, so it just gives you the sample variance. I already mentioned once that the difference between the variance and the standard deviation is just going to be the square root of that. So we're not going to have to look it up very often. Actually, I take that back. That is not your sample variance. I shouldn't have circled that. I'm sorry. The way you're going to get your sample variance is you're going to find your standard deviations and you're going to square them. So sample standard deviation is the S, and that one is right here. Population standard deviation is the sigma. Notice that in the last slide these were squared. This one they're not because you've got the square roots. And the sigma is right there. So this is your population standard deviation. This is your sample standard deviation. Again, I apologize, that thing there was not the variance. The way you get your variance is if you take then these numbers and square them, that would give you the variance. So if I ever ask you, well, what's the variance? Which I won't be asking that very often, maybe once. You would just take and you would square these numbers. This is the one we use most often. And the reason why they're not the same thing goes back to that little tweaking of the formula between the n being the population number and the small n minus 1 sample minus 1. So here again, you don't really need the formulas. All I really need you to know here is that you can find them in single variable stats. You do want to take notes on which one is which. S is the sample, sigma is the population, and maybe make a note that if you want the variance, you have to square the standard deviation number. Okay, so maybe keep track of that. Okay, this is just me saying the same thing all over again. Here's something else for you to know though out of your graphing calculator. Other than the standard deviations, you can also scroll down, and we talked about the range. If you have data in your calculator and you do single variable stats, it'll tell you the minimum and the maximum numbers in your list. This would be after you've entered the data in the lists. And this is especially if it's a really big list of numbers, it might be hard to actually just look at it and pick out what's the most, what's the least. You know, if it was 10 numbers, you could probably figure it out. But if it's a lot of numbers, then it's hard to just look at it and know. But your single variable stats will always tell you the minimum and the maximum. Notice the median is in there. All right, let's get back to talking about the standard deviation. I told you standard deviation is going to be the one that we consider the most. And it's because the standard deviation has been shown to actually give us some information, some useful information. And on this slide, these are approximations, but it's still useful information. If we know the average, the mean of a set of data, and we calculate the standard deviation either by hand with the formula or getting the standard deviation off of our single variable stats, if you go one standard deviation up and one standard deviation down, it's going to be really close to covering, if you just add these two numbers together, 34%, 34%, that's 68%. 68% of the population of whatever it is you're studying, as long as it's a normal distribution, this does have to be true, it's got to be a normal distribution, 68% will be covered within one standard deviation away. This is a little confusing because when I say one, you might be thinking, well, there's one going up and one going down. But when I say one standard deviation away from the mean, that includes both up and down. Up meaning in the positive direction, down meaning in the negative direction. So numbers getting bigger, numbers getting smaller. Not necessarily negative numbers, just getting smaller. Now, in more practical terms, if you're studying something and something falls in this area, the variation there, we can say, well, you know, that's what most of things are happening at. The stuff that's in this area is kind of high, so most of the things are probably less. Over here, that's kind of low, so most things are probably more. Down here, getting really small. Not many things are way out here. So definitely, most things are more. If it's up here, definitely most things are less. I think they actually have that worded a little bit funny there, because here it is, most things are going to be less. So you can actually talk about, hey, is this weird more? Is this just kind of about the same as everything else? And so we can actually start assigning number values to those kinds of statements. When you say things like, hey, most people like hot dogs more than hamburgers. Okay, well, let's go study that. Does the standard deviation say that? If we have the average numbers and we're comparing them, we could go one standard deviation up, one standard deviation down, and see if it is actually most. Maybe it is, maybe it's not. Quite frankly, I think that one's probably false. But that's the idea. We can start to actually talk about, well, what is most? What does most mean? And we take these somewhat vague terms and we assign numerical values to them. So unusual. Here's a question. So here we're looking at yields and yield trends for corn between 1996 and 2011. The question, well, is that unusual? That one seems to be kind of far away. Well, we can go through and we can take a look. You put together all of the numbers into your calculator under stats and then do your single variable stats. And this is actually that set of data right there. The average, the mean, was 143.4. We'll just call it that. With a standard deviation of, and I'm going to use, I think I used this, 11.73. Okay, so what would be unusual? Unusual is considered anytime it's more than 2 standard deviations away. Now you might wonder, well, do I add it or do I subtract it? Well, you got to look at the data for that. This one's above. So I was like, well, how many standard deviations away? I know this is not drawn out as a nice bell curve, but it's still, how far away is it? So I want the plus, I want to add it because it's above. If it had been down here someplace, well, then I would want to subtract. So I'm going to take and double the 11.73. After that, I'm going to add it to the mean. When I get that, I get 166.8. So is the 160 unusual? I would say no, because 166 would be like farther away. And it's not considered unusual. Please make note of this. It's not considered unusual until it's more than 2 standard deviations away. I'll say this, 2 standard deviations or more. I'm not going to give you one that's exactly ever 2 standard deviations and make you try and, make that decision. That's kind of where common sense has to come in with a statistician. They have to really kind of look at, well, make some choices. How many data points do we have? Things like that. But I will be asking you if something's unusually high or unusually low. In that case, you get the standard deviation. You would double it and either add or subtract to the mean and then see if your data point is beyond that or not. In this case, it's not. So this is not an unusual year that year. It just, on the data, it looks like it might have been. Okay, I've sort of been leading up to this. These terms usual, here's that term right there, usual. So you got usual and unusual. Unusual is when you're more than 2 standard deviations from the mean. Now I'm using the population mean symbol here. I could have just as well used the sample mean, but typically with this kind of conversation going on right now, we're talking about the entire population. So I'm looking at the population mean. And the empirical rule goes like this. It's approximate. In fact, I'm going to go to another little interactive thing here. So here's just a normal distribution. This one has a mean of 100 and a standard deviation of 16. So what you're seeing here is from 100, you could go 16 above and 16 below, as would be considered. Now that's most of the population. And here you're actually seeing the exact numbers. We normally round this to 68, but the actual number is 68.3. 68 is close enough though. A true statistician's not only going to look at the numbers, they're going to look at the approximate numbers and use a little bit of common sense. But there's 1 standard deviation away. Let's look at the variation being farther out. 2 standard deviations. So notice we're measuring the variation. 3 standard deviations away. Standard deviations being again related to the variance. 3 standard deviation covers almost the entire population, 99.7%. You're going to see these numbers over and over again throughout this class. 68% is typically how I'll round that. 95.4 is actually pretty normal, but you might see it as written as just 95%. The third one's almost always written as 99.7. So 68, 95, 99.7. If data goes beyond the 2 standard deviations away, because that covers 95% of the population, that it's then considered unusual. Okay, so that's what I'm showing you here. So I put these about numbers in here. Yes, I know it's technically 68.3, but it's about 95%. And anything beyond 3 standard deviations is considered rare. That's a rare event. You know, we start to talk about probabilities now. What's the probability of getting struck by lightning while I'm driving in my car and eating an ice cream cone? I gotta believe that's a rare event. And so you'd have to analyze that kind of thing. But so we've got unusual. In here is most. I didn't write it, but most. Out to 2 standard deviations is usual. That's what I would probabilistically usually find. And then beyond that is unusual, and beyond that is considered rare. So when you look at, again, media with a critical eye towards misleading statistics, be aware that these words actually mean something statistically. It's not just anymore these vague terms where I say, well, I think that's a rare event. Well, it's not a matter of what you think. It's a matter of how far away does it fall from the average event. And of course, I don't have it in here, but this is the most area. 68% of a population is within 1 standard deviation. I'm going to give you an example here. The top part is something that's actually in this section. The bottom part is going to be, I'm going to go a little bit farther than what this section does, and you're not going to totally get it, but I just want to show you this example here in relation to making calculations with standard deviation. Okay, so I've got some information here, some statistics. The height of men have a bell-shaped distribution, so they're normally distributed, with a mean of 69.5 inches. Okay, so I think it's not 6 feet, it's a little bit shorter than 6 feet. The standard deviation is 2.5 inches. So if you calculate from the data, the standard deviation is 2.5 inches. Use the empirical rule. Okay, so that's that 68% and then so on and so forth. What is the approximate percentage of men between 67 inches and 72 inches? Okay, so what you're going to want to do here is 1 standard deviation away is 2.5 inches, which I could then, if I add 2.5 to this, that would give me 72. There's that number. If I subtract 2.5 from this, that's the 67. Okay, so I'm just going to use this chart here. So the mean here was 69.5, 69.5. So you can see visually what I just did. If we go, what's up to the next line here, 1 standard deviation away, it would add the standard deviation, 2.5 inches. And again, this number comes from a calculation using that formula. What if I went in the opposite direction? So subtract 2.5 inches. That gets me down to the 67. So then back to the question, what's the approximate percentage? Well, that'd be 68% of the population. 68% of men, and I believe this statistic is U.S. men, and it's a little bit old. It's probably a little out of date, but when this was gathered, I believe it was men in the United States, were 68%, or most of them, are between 67 inches tall and 72 inches tall. This I would expect you to be able to do today. So there'll be stuff like this in your assignment. Now, I'm going to take you a little farther. This is not from this section, but I'm going to ask this question. Michael Jordan, everybody knows who Michael Jordan is. if Michael Jordan is 6'6" or 78 inches tall, okay, he's a pretty tall guy. But when you see him out on the court, he's not the tallest guy. He's tall, but man, a lot of guys taller than him. Approximately what percent of the population is he taller than? So now I'm going this direction because this is the tall side, the bigger numbers. This is the small side, the shorter numbers, people that are shorter. We're going in one direction here. Well, what we can do is we can do this. There's a formula here, and you don't quite, I know you're not going to know what this formula is yet. Just hang with me. I'm going to calculate a number here, and this is going to tell me how many standard deviations his height is away from the mean. That's what this is going to tell me here. So I take his height, subtract the population mean, divide it by the population standard deviation to give me the standard deviation for Michael Jordan. That's all I'm going to do here. His height minus the population's average height divided by the population standard deviation. And Michael Jordan was 3.4 standard deviations away. Now remember, so we got 1, 2. That fell under usual. And then we got 3, unusual. So that's getting pretty far up there. And notice this one actually has numbers here. Now I have 3.4. This is actually 3. So I actually didn't quite do this right. It would be a smaller number because it would be actually 3.4 would be even less than that. He would have the taller than him. I'm guessing it's closer to 99.9 if I was to take an educated guess here. He's approaching a rare height. You know, you watch him on the basketball court. All those guys are crazy tall. They're some of the tallest men in the country. And so it's definitely an unusually tall man approaching rare, almost not quite. Rare would be 99.7. And he's not quite there, but he's actually, I take that back. He isn't there. I'm sorry, it's rare. He is beyond that. So his height is actually a rare height. It just doesn't show up on TV because it's tough to, on a screen, be able to approximate the height of a person. All right, moving on. Not everything has a normal distribution. So what do we do if it's not normal? Like this one here. This is a bimodal one here. You cannot use standard deviations when you talk about bimodal or trimodal or anything like that. And so the best we do is we approximate with something called Chevyshev's theorem. Chevyshev's theorem. Strange to say. Go ahead and pause. Give it a try if you want to try it. Just a weird word. It's a man's last name. Unlike the empirical rule, again, the empirical rule, it had to be bell-shaped. If it's not, you got to use this to talk about standard deviations. The values are approximate since they use lower limits, and the theorem will have limited usefulness. What I mean by that is most of the time we're going to be looking, at least in this class, we're going to be looking at normal distributions or bell-shaped distributions. And I'm not saying Chevyshev's theorem is not useful in real life. I'm saying for this class, we're not going to run into it much. But in real life, yeah, there's a lot of distributions out there that are not bell-shaped. Chevyshev's theorem, the proportion or fraction of any set, I'm going to read some stuff here. It's a lot of the theory behind it. Just hang on for a second. It's really not that hard to use. Of any set of data within k standard deviations of the mean is always at least 1 minus 1 over k squared. You do not need to write this down. Where k is any positive number greater than 1. For k equal to 2 and k equal to 3, the following statements. Okay. So when k is 2 or 3, at least 3/4 or 75% of all values lie within 2 standard deviations of the mean. At least 8/9 or 89% of all values lie within 3 standard deviations of the mean. So when you're given questions about Chevyshev's theorem for this class, you're going to be either 2 or 3 standard deviations away, and you just have to figure out, well, that's 75% or 89% of it is what you're going to do for this class. We're not going to do a lot with Chevyshev's theorem in this class. Let me give you an example, though. what we're looking at here has to do with IQ scores, and these IQ scores were taken from SAT scores to assign them an IQ score value. We're going to apply Chevyshev's theorem to the mean score of 100. Okay, so there's our mean. We've got a standard deviation of 15. By the way, just a side comment, I find it interesting that IQ scores are not a normal distribution, at least not the ones that are pulled from SAT scores. I think that has to do with because there's such a small population compared to the entire population that take SAT scores. Some of them are on the East Coast, some are the West. The Midwest doesn't usually do SATs, so they're a smaller population. And you're really just looking at those looking to go to college, which leaves out about 2/3 to 3/4 of students don't take the SAT that are even living on the East Coast or West Coast. So because of that, it ends up being a non-normal distribution. Okay, back to this though. I want to know what are the IQ scores that are within one standard deviation away. Okay, so what I'm going to do here is we're going to take and at least 75% fall within 70 and 1/3. Where am I getting that? Well, I got to double this. Standard deviation is 15, twice that, so that's 30. 100 minus 30 is going to be where I get that 70 from. 100 plus 30 is going to be where I get that 130 from. If it's farther out, then 89% of the IQ scores fall within. Okay, so now we're going to go 3 times. 3 times 15 is 45. So 100 minus 45 and 100 plus 45. We're on this one. 100 minus 45, 100 plus 45. Still the same idea. I got to triple it this time. Will give me 89%, which 100 minus 45 is 55, and 100 plus is, of course, 145. That's Chevyshev's theorem. We'll use it a little bit, but not very often in this class. All right, give some problems a try, practice them a little bit. Have a good day.